Okay, one slide, quick summary, what we learned last time, right? So we talk about now stress at the point. We are doing stress analysis. We're not looking at a structure, right? A bar or shaft anymore. It can be anything in a structure, any structure. Inside the structure, at one point, we talk about stress at that point. And we look at the one special situation, a simplified situation. We call it, anyone remember what's the term? 2D. We talk about 2D, special 2D situation, right? Easier. Plane stress, right? So plane stress is basically you have a 2D situation, right? The third dimension of the structure is very small, like a plate. And so therefore, all the stress in the z direction, in the thickness direction, are zero. No stress in this direction. So that we call that the plane stress. And then we talk about if you have this structure under load within the plane, right? So all the stress are within the plane. Now, if you rotate the coordinate system where you're observing, or let's say you give any direction you want to figure out the stress in that direction, here's the equations, right? So because in general you're going to have sigma x, sigma y, and tau xy. So therefore your equation on the right side, you have three terms, sigma x, sigma y, and tau xy. And when you rotate in that new direction, in general you're going to have a stress, a normal stress, we call sigma x1, and then you're going to have a shear stress that called tau x1, y1. But in that another direction, 90 degrees from it, so when you look at the block, the other x direction, you're going to have a sigma y1 and also tau x1, y1, right? Because we know on that element, the shear on four sides has to be equal, otherwise it won't be equilibrium. Okay, so that's the equation, convert the stress from the old coordinate system to the new coordinate system. So therefore we can call transformation equation, right? But also this you can interpret it as an equation you can use to calculate the stress in any direction, the normal stress and the shear stress. Okay, so today we're going to follow this, talk about, two things. One is when you rotate, imagine you're just looking at all different directions. Okay, which direction give you some, say, maximum normal stress or maximum shear stress? Because we know some material will fail by shear, some material will fail by tension. So then different material, they may fail this direction or they may fail the other direction. So that's why we need to figure out in which direction you're going to have maximum normal stress and maximum shear stress. That's the first part. The second part will be we'll look at the Mohr circle. How can we use the Mohr circle to help us determine all these quantities? Okay, first one, you have this expression here. Sigma x1 equals, look at the first equation. Sigma x1 equals that expression now. Okay, now when you change the theta, your sigma x1 will be different, right? It depends on theta. Okay, now when you change the theta, in which theta angle this will be maximum? How do you determine? Immediately something 45 degree. We had something 45 degree before, right? It may be something related to 45 degree, but not necessarily 45. So this is basically a mathematical question, right? You learn it in, EA calculus. How to determine the maximum value of a function. This is sigma x1 is a function of what? Function of theta, right? So if you look at it, so sigma x1 is basically a function of theta. Now how can you determine the maximum of a function? Take a derivative, right? We all know. Okay, so let's take a derivative of the first equation. Find out what's the theta value that gives us the maximum normal stress. Then we can take the derivative of the last equation, find out where the tau is maximum. Okay, let's do the first one first. Okay, so first equation, you do the derivation, right? Now, derivation to theta. Okay, what's the first term? 0. Okay, so it's gone. So what do we end up with? This equals 0. You agree that? Sine, when you do derivation, cosine become cosine. Cosine become negative sine, right? So the 2 come out. But the 2 both has 2, so you can you end up with this equation. Okay, so from here, can we find out theta? Yes, so that will be the result. The tangent of the 2 theta equals that. And this direction, okay, we give a name about this direction. This is the direction that is the normal stress become maximum. So therefore, we call it principal direction. The stress in this direction, we call principal stress. Okay, so the principal stress is the maximum stress. Or you can say maybe the minimum. Yeah, possible. Maximum or minimum, right? It's never, bless you. So it's never in between. So it's either maximum or minimum, right? Okay, so that's the principal direction. All right, now, in this direction, the theta value you determine by this last equation there. Okay, and in this direction, this equation here, this is true, right? Okay, what does this mean? Now let's look back here. Okay, look at the last equation here. Is this the same equation as we just saw there? Except you put a 2 there. If you multiply 2 to the last equation, it's the same equation? Okay, so therefore, what does this mean? This means, okay, your tau at this theta p direction will be equal to 0. Because this is the tau. And it must be 0. Because otherwise, you won't have the last equation and you won't have this derivation equal 0. Okay, what that mean? That means this principal direction is really a special direction. In this direction, you only have the normal stress that takes maximum or minimum. And the shear on this surface is 0. So in the principal direction, there are only normal stress. There's no shear. All right? Okay, now, if this is true, right, you can take it back. You can actually calculate sigma x1. What's the sigma x1 value? So here is a explanation what that 2 theta p mean, how to calculate it. Right, so that's the equation. All right, and here is the stress when in the principal direction with the theta p equals that value. You take it back to the sigma x1 equation. This is what you get. So you get the sigma value will equal to either the top one or the bottom one. So we name it sigma 1, sigma 2. So what's sigma 1, sigma 2? It's the principal stress. So it will be maximum or minimum, right? Actually, you have 2 solutions. One sigma 1, that's the maximum. And you have another one, that's sigma 2, that's the minimum. So we have one solution is the maximum, one solution is the minimum. Okay. So when you rotate to this special angle theta p, you're going to have only a maximum stress, no shear here, only this one, only a maximum stress. And then if you go to another direction, so when the theta p change by 180 degree, you have another solution for the same equation, and that is a minimum. Sorry, let me take this back. Okay, let me draw it here. It's better draw this. So if I go to this theta p, this direction here, so this is a theta p angle, right? So this is theta p. Okay, you're going to have sigma 1 here, and there's no shear on this surface. So that's the first solution. So we call this sigma 1. Okay, so what's on here? What's the value here? It's a sigma 1. You have to be, right? Action, reaction on 2 sides to be balanced. That's why I'm taking that wrong statement back. Because on this side, you have sigma 1 as well. And where's the sigma 2 solution? It's here. So that's a sigma 2. So when you go 90 degree more, the 2 theta p actually go 180 degree more. But the theta p itself go 90 degree more. So from here to here, that's a 90 degree difference. You're going to have sigma 2. All right. So the principal directions, there are 2 solutions, 2 directions. One is the sigma 1, you have the maximum. Another one is 90 degree from it, that's a sigma 2. That's a minimum value. And so you have 2 principal directions. Actually, they're 90 degrees apart. So once you give me one, I know the other one. Right? So when you solve a homework problem, you can just give me one. Say, oh, it goes this much. That will be the maximum value. Right? Now I know, oh, at 90 degrees will be another one. All right. Okay. So any question about the maximum minimum? So here is just another way I derive what's the maximum for shear stress. Okay. How can you get the maximum for shear stress? Same thing. We do derivation to theta equals 0, right? And then you solve it, so you get this equation there, right? So the conclusion is, all right, if this is sigma 1 direction, then we know this will be 90 degrees away will be sigma 2 direction. Then between them, 45 degree. Here's the 45 degree coming out. 45 degree, that's the maximum shear stress direction. So the maximum shear stress direction is 45 degree away from the principal direction. Okay, from the principal direction, not from your x or y direction. So if you find your first principal direction, then 45 degree away, that's the maximum shear direction. And then another 45, so 90 degree away, that's your minimum stress, the sigma 2 direction. So that's how the spatially they are related. All right. Okay. So this is a clear picture in your mind, set up. Right. So let's say you have an element here. You have some stress here. Maybe this compression even, right? Can be a compression or tension. And then you have shear stress here, right? Shear stress here. All right. Then at a certain degree, let's call this one theta p. Then in this direction, you're going to have sigma 1. Then must be 90 degrees away from it. This will be the sigma 2 direction. Okay, then the shear. So this direction here must have the tau maximum. That's the relation. Okay. Now, what about this direction? 90 degrees from the tau maximum direction. What's the shear stress there? Right? Let's say if I draw an element this way, so this is the tau maximum, right? So if I draw an element somewhere here this way, so this is the tau takes maximum. Tau takes maximum. So what's the tau here? Can it be 0? No, if it's 0, you won't be in balance. There will be movement. Must be no shear. So what's the tau here? The same exact same amount maximum. So if this is the tau maximum direction, then if you go 90 degrees away, either way, this way 90 degrees or this way 90 degrees, that's another tau maximum direction. All right. So you have basically in this 360 degree, somewhere you have a principal direction, right? This is the one principal 1 direction. So you go this way, this is 2 principal 1 direction. Then 90 degrees, that's a 2 principal 2 direction. And then between, this is the maximum shear direction and the maximum shear direction. That's how they related spatially. All right. Okay, that's a clear enough picture.
Does that max change if the forces are different? The compressive force is 100 and the tensile force is 1,000. Does that change?
Good question. Will it change? If the normal stress, or the sigma x, sigma 1 is positive or negative, will it change? The answer is yes. When you have, say, the same value, but different signs. The reason is here. This is the equation you calculate the shear stress, right? When you have sigma y, the same value, but you change sign. So then here, the value will be different. So therefore, your answer will be different. Right? Okay. All right, so now what's the maximum shear stress? It's actually given by this equation. Right? So, and from here, you actually can clearly see, if you change the sigma y from a positive 5 to a negative 5, see, this value will be different. So your answer will be, maximum shear stress will be different. So sign doesn't matter. here. All right. Okay, any other questions? Okay, what's R? Okay, I haven't explained what's R yet. R is a Mohr circle radius. So we're going to talk about R. What's R? What's the circle next? Okay. I kind of reshuffle my slide. I want to give you this, follow the equation, give you this mathematical derivation first. Then we talk about visually how to draw the circle. Right? Okay, so let's say what's R, and we'll see it there. The R actually is just this equation right here. But why you call it R? Okay, so I explain more circle next. Okay, any questions about this? Where's the principal directions, the maximum shear? Or spatially how they distribute, right? Remember this 90 degree away, two principal directions. And then in between, that's the maximum shear direction. That means in this direction, if you look at surface there, on the surface, there is maximum shear stress. Okay, any questions here? All right, now let's look at the Mohr circle. Okay, so we said last time, the stress, if you look at the equation, this looks like an equation of a circle, right? So now, first, how do you draw this circle? Second is how to use the circle to find the principal stress, the principal direction, maximum shear stress. That's what we needed to find. Of course, you can use the equation I just gave to you, right? We just talked about it in a second ago. But also, you can just use the circle, just show it to you. Visually, you can see it. Okay, how to draw a circle? What do you need to draw a circle? You need a what to draw a circle? You need a radius, okay? What else you need? Origin, the center. Where is it located? Right? So fundamentally, you just need these two things. You can draw a circle. All right, now this is the equation of the circle. So where is the center of this circle? Where is the center? See, this is like the x, right? This is like the y. Right? Because when you change x, y. You change sigma x and the tau x, y. So we're going to draw a plane of tau x, y. So this will be tau x, y. And then this will be the sigma x. So we talk about this plane. On the plane of sigma versus shear stress tau. On this plane, right? So that's your x, that's your y. So it's x minus, is this equal to, I think I have this equation here. Is this equivalent to this equation? Right? The top equation is equivalent to this equation. Your variable is sigma x1, that's your x. Then you have the tau xy, that's your y. Are these two equations similar? Okay, now where's the center of this one? X minus a for this one. Where is the center? Where is the center? When you have this equation, I think we talk about if x minus a squared plus y minus b squared equal to r squared. Where is the center? A and b. Okay, now in this case, what's the b value? 0. So therefore, your center is supposed to be at a0. So we find the center. Now we need a radius. What's the radius? This is the radius. That's the r squared. So therefore, we have the radius. R squared equals that. So we can draw the Mohr circle. Right? Okay. Everyone can draw this circle now. Because when I give you a sigma x, sigma y, tau xy, so you know all this. You can calculate it. And then you can calculate the radius. So you can draw the circle. Right? And we know when you, see, if I give you this element here, right? I give you sigma and tau. So this will be sigma x, this will be tau x, y, and then you have sigma y here. So if I give you this element, I know the sigma x, sigma y, and then tau x, y. You can draw the Mohr circle, use this equation. Because you know where the center is, where's the radius, so you can draw it. So draw this circle is not really not hard at all. Now, how can we use this circle? Sometimes it's. Okay, let me ask this first question to start how to use it. Okay, if I draw this circle, let's say it's shown here, right? Now, at this element, if I have this x, y coordinate system, right? Right now I have sigma x on this surface. Let's look at this surface. I have sigma x and tau xy on this surface. Is that correct? Now, how can I find this point on this circle? So this direction, this is the x direction. I have sigma x and tau xy there. Now, where is this point located on this circle? You need first, okay, sigma x, let sigma x equals 20. So you go here, find out, okay, here x coordinate, this is 20, right? And then you look at the tau, let's say it's 10. So you go up 10. So that's your point. That's the point A, surface A. This one, we call this A surface. Is that correct? How do you locate the point on this plane? Basically, the two coordinates, sigma x and tau xy. That's your x and y.
So you said you go up 10.
Yeah, okay. I said I go up 10. Why I move down 10? Because my coordinate here is a weird, strange coordinate. This y is pointing downward. See here, this is my point, positive y direction. Okay. Why I'm doing this way? Two reasons. One is the guy started this doing this way. All right? And his name is Mohr. That's why we call Mohr circle. Okay. Why he pointing downward? There is a reason. He's not just randomly put there. He would like to use the counterclockwise as a positive direction. All right? That's the reason. So if you point this way, you use positive direction as counterclockwise. It match your surface here. If you go this way, that's a positive angle. So here you go this way, it's a positive rotation, positive direction. Okay. And everyone be used this way. So therefore, if you just change it, okay, nobody or no other engineer, they're not using this way. So you don't want to change it because that's kind of becoming people used to this way. All right. So remember now, we have a coordinate system, y is downward. That's why I say I have a positive 10, so I move down here. So this is my point A here. All right. So at this point, the coordinates is actually sigma x, and then this will be tau xy here, the point A. Okay. In other words, my current x direction is here. This is my x direction. This is my x direction here. This is the x direction. It's corresponding to this direction here. All right. So that's my baseline right there. Okay. Now, if we want to draw a circle, we can use the center and the radius. What's the other method you can use? How about if I know 2 points on the circle as a diameter? Can I draw this circle? Yes, you just rotate, right? So that's another way. So therefore, okay, an alternative way, or method 2 of drawing this Mohr circle is you label this point A here. Can you always find the point A on this plane? Yes, because you can always know sigma x and tau xy. So you can always pinpoint this point. Okay, now I need another point on the opposite direction here. Okay, where is this point? Okay, I say that is sigma y and tau xy. Okay, I explain why it is sigma y and tau xy. Okay, anyone has an equation y? The reason is, okay, how much angle you need to rotate from A direction to the B direction, from OA to OB, and not OA, CA to CB. How much degree you rotate there? 180. Okay, now you rotate 180. Remember our equation. Okay, say this equation. Oh. Okay, this is the equation. When you rotate 2 theta. So when you go from this point to the other point, when you do the calculation, you put this wall, you put add 180 degree, right? Now for theta, you add how much? You add 90 degree, right? Yes. So therefore, from CA direction to the CB direction, you actually add theta of 90 degree. The theta change 90 degree. Okay, from this OA direction, let's go back to this. Okay, so from the OCA to CB direction, you rotate 100 degree on this plane, but your theta changes 90 degree. Okay, now from here, look at this physical plane, this plane again. Theta change 90 degree. Which direction you are in? You're in the y direction. That's why I know this stress must be sigma y and tau xy. Okay, so here's the explanation part. It's maybe a little bit hard to follow. Okay, but the conclusion is actually very easy. Okay, so how do you draw the Mohr circle? Okay, so what you can do, this method 2, I'm summarizing. Okay, the method 2 will be you mark 2 points. One is point A, and one is point B. Okay, so point A is a sigma x tau xy, and point B is a sigma y negative tau xy. You can always draw these 2 points. One on the bottom half of the plane, another one on the top half of the plane, right? Your dividing line is at sigma x axis. So you basically, here is your coordinate, sigma direction. This is the tau direction. So where you draw this Mohr circle, first you find out this is point A, will be sigma x, and then this will be tau xy. Now your next point, point B, will be somewhere here. Okay, so this will be sigma y, and then negative tau xy. So therefore, this distance here, this distance here, they are equal. One is positive tau xy, one is negative tau xy. Okay, then you just draw a line between them, and that's your diameter of the Mohr circle. And then you can just draw the circle with this diameter. That's it. Okay. So although when you draw the Mohr circle, the method 1, you know the center. And you use the center, you draw the circle. It's easier, right? With the radius and the center. But because later on we need to find out sigma y, sigma 1, sigma 2, the principal direction. So you still need the A point. So for this reason, I feel my recommendation is use method 2. Because you need this point anyway. So why just directly start with AB and then you go ahead and use for later on, right? Because all the angle theta p, will refer to this principal direction. And you're going to need this OA direction to be calculated. So let's say this is the principal direction. So your theta p will be this angle. This angle is your theta p. You start from the x direction. Okay? And in fact, this angle here is actually 2 theta p. Why is 2 theta p? Because all the angle on this plane, the Mohr circle plane, or the Mohr plane, is 2 theta. Everything double. Because the equation starts with 2 theta. Therefore, everything now on this plane will be 2 theta. All right? Okay, so now we know how to draw the Mohr circle. You just use point A and point B. Now, on this circle, where is the direction that the normal stress is maximum? The shear stress is 0. On this circle. See this, let's see, make it better. This is the circle. Okay, on this circle, which point that the normal stress is maximum or minimum, but the shear stress is 0. Which point? Is it this point that the circle crosses with the x, the sigma axis? Okay, what's the stress, shear stress here at this point? 0. So there must be the normal stress, that maximum. So that's the principal stress. In other words, this is the sigma 1. Okay, where's sigma 2? Right here, this crossing point, sigma 2. Now, where is the maximum shear? On this circle, you have a circle, right? So this direction is the level of the shear stress. Now, where is the maximum value? Which point? Where the peak is? Where this peak is? So the center, this is the center, you draw a vertical line. That must be the maximum. That's the peak, highest point. And of course, this point is the same. One is positive, one is negative. But for shear, it doesn't matter. The value is that much. Okay. Now, based on this, all right, if you draw a Mohr circle, can you quickly find out the sigma 1, sigma 2? Can you find the shear, maximum shear? Okay. Now, what's the value for maximum shear? What's this value? Or what's this value? R. So I can say the conclusion will be tau maximum equals to R. That's where the equation you saw before. Right? Okay, now what's the sigma 1? Maximum normal stress is equal to the center plus an R. This point, sigma 1 here, is equal to R plus C?
Yes.
Yes. Okay, now what's sigma 2 then? Will be C minus R. So once you have the circle, all this maximum value really easy. You look at the circle, okay, so C plus R, C minus R. That's why people are using Mohr circle, because very visually you see it quickly. All right. Okay, any questions? All right, this may be a little bit too theoretical, right? You guys like example, so let's use a couple examples. Just say, how can we draw the Mohr circle? Then use the circle, find out sigma 1, sigma 2, and the tau maximum, and also sigma p, theta p. Right? Okay, let's go over some examples. All right, here's one example. So we have a point in an object that's 2D, so plane stress. So at this point, you have normal stress in the x direction, but actually happen to be compressive, so negative 50. We call that negative 50, right? So if you write it in word, it will be sigma x equals to negative 50. Okay, what's sigma y? Negative or positive 10? Positive 10. Okay. What about tau xy? Positive 40 or negative 40? On positive surface, point to a negative direction. So that's negative. So it's negative 40. All right? So I can give you a homework problem. Either I show you this picture, or I can use word, just give you these values. These two are equivalent. So you need to know both from the word and from the picture to find your information. Okay, so that's one requirement for you. So you need to know the sign convention, in other words. Which one is positive, which one is negative. All right? Okay, now for this stress condition, you have here, for this point. Okay, how can we find the Mohr circle, draw the Mohr circle, find the sigma 1, sigma 2, right? So we care about sigma 1, sigma 2, and also tau maximum, as well as theta p. We want to find out which direction giving me the maximum stress. and also which direction gives me the maximum shear stress. All right. So let's draw the Mohr circle. So start, you set up your coordinate system. So this is the sigma direction. This will be the tau positive direction. Make sure it's pointing downward. Weird, but we need to follow this, get used to it. All right. All right, so we need the coordinate system set up. So here's my 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. Okay, so every tick there representing 10. Now, how can we get the Mohr circle? You can first find the center and the radius, draw it. That's the option 1, right? Or you can find the point A and the point B as the diameter, draw it. Okay, I would like to start with the method 2. So you want to find the point A and point B. 2 points on your circle. Okay, where's point A? Anyone remember from last slide? Where's point A? Sigma x. So let me write one more step here. Sigma x, tau xy. Okay, so therefore is what? Where's A? What's the value? Sigma x. So negative 50, then negative 40, right? Okay, where's the point B? Sigma y and negative tau xy. So where's that value? What's the value? Sigma y, 10. Negative tau xy, positive 40. So you have A and B point now. Now, can you label A and B on this plane? Yes, okay, let's find out A first. A, negative 50. So 1, 2, 3, 4, 5. So 50, negative 50 here. Then negative 40, right? Okay, where's the negative 50, negative 40? Go up or down? Go up. That's a negative direction, right? So 1, 2, 3, 4. So here. So that's the point A. Everyone agree on that? Okay, now can we find the point B? Where's the point B? 10. Okay, so here's 10. Go up or down? Down by 40, right? So here. This is my point B. Okay. Now, can we draw the Mohr circle? Yes. Get the connected line. Okay. So A and B. Connected. A to B. Now, this will be point C, right? So point C always on the x-axis, on the sigma axis. Right? So if you draw a Mohr circle somewhere here, I don't even need to spend time. I know you're wrong. Because you're away from the sigma axis. So never draw a circle that's off the sigma axis. It's always moving around the sigma axis. So if you draw it somewhere there, that's definitely wrong. Okay, so this won't be there. All right, now we can draw the circle. So we draw the circle here. All right. Okay, what's the C value? Where's the C? Point C. By just look at it, I can say it's negative 20. So C will be negative 20 and 0. Okay, am I correct? No? Okay, how do you calculate C value? Should be, see here, point A, positive 10. Point B, negative, what? Negative 50. So how do you determine C? C is supposed to equal to half sigma x plus sigma y. And what's the value? Negative 50 plus positive 10. So that's negative 40, but you have to divide the 2. So what's the value? Negative 20, see? The visually is show correct. So that proves you can visually see, get the value, or you can calculate, get the value. Okay, because you want to visually read the value, make it reasonable. So when you draw the Mohr circle, carefully set up your coordinate. Make it proportional. Don't make this side 10 is this big, the other side 10 is this big. Your circle will be screwed, and if you draw it, you won't actually read the value. So you set up the correct, proportionally set up the coordinate system. All right, so that's one suggestion. Okay, so we have the correct C, that's 20 here, and negative 20 here. All right, so we finished the Mohr circle. We have a circle here. Now, from this circle, can we find out what's the maximum shear? What's the sigma 1, what's the sigma 2? Okay, where's sigma 1? First label it. It's right here. That's the sigma 1, right? This is the sigma 2. Where's the maximum tau? If you draw this line here, so this point or this point, it should give you the same, the radius. Okay, so the key information we need now is what's the radius? Okay, which line is the radius? I'll say this line is the radius, right? This length is the radius. Okay, how do you determine this length? See here, we have a perfect triangle. Or you have another perfect triangle here. Can we get the radius from this one of these triangles? Okay, side square, add together. Okay, so what's this length? 40, right? Okay, what's this length? 30. Okay, 3, 4, what's here? 5. You don't need a calculator, right? So radius will be 50. Okay, so R equals 50. Now, if R equals 50, now what's the maximum shear stress? What's the maximum shear stress? 50, right? Now, what's the sigma 1? $30. How do you get 30? You start with the center, negative 20. Then you plus R, 50. So you end up 30. Okay, now what's sigma 2? Negative 70. Negative 70. Okay, now the last question, or the most challenging question. What's the theta p? The direction from your current x direction, this direction here, right, to your principal direction. First, can you label on the circle which angle you're looking for? Is it, say here, this is a sigma 1 direction. Sigma 1 is right here. So should that be this angle? Because you're OX, this is the x coordinate. This is your x direction. So from this x direction, you root this much angle, you get to the sigma 1 direction. So you need to look in for this angle. Right? So this is my 2 theta p here. So you first visually you label, oh, where is the theta p? 2 theta p. Next is how you find it, calculate. Okay, first you all agree this is a 2 theta p. You all agree on that?
Is it from the x?
From the x, OA, right? See, from CA, that's your current x direction. See, point A, it means the x direction. So your OA, that's the x direction. Yeah.
I'm wondering why x direction is not.
Okay, what's the x direction? X direction is the physical on the physical plane. Let's distinguish them. This is your actual physical plane, right? This is the Mohr plane. So you have 2 planes now, right? So the x direction is on the physical plane, the x direction. On that surface, you're going to have this stress. So this point is here. Because this value, A, how you determine A is here. That's why on the Mohr circle, your point A is at that location. So your A direction, the x coordinate is from the center C to A. Because when I rotate all this direction, every direction corresponding to a direction on this plane. Got it?
Basically, X direction.
Yeah, X direction is where the A is. Yes. That's why I prefer use the second method. You immediately label, oh, here's A. So here's the X direction. That's your starting point on the physical plane. Right? So, in other words, this X here corresponding to this X here. All right? Okay, once you realize this, next will be easy. What you need, you can calculate the value. So can you determine this angle? Yes. That's what, like maybe 68 or something degree, right? 3, 4, 5. You can use calculator, get the arctangent. Right? This is 4 here. This is 3 here. So what's this angle? Anyone get the calculator? You can quickly get it. I think it was 68 or something. Okay, got it? So the tangent is 4 divided by 3. 1.333. That's the tangent value. 56 degree, right? Huh? 53. Okay, so this angle is here is 53 degree. Okay, now what's 2 theta p? It's 180 minus this 53. Now what's theta p? Divided by 2. All right. So use Mohr circle is really help you to determine the angle. Okay, if you're not sure, write down this value. Now go back to these equations. See here, we have the equations. Here, we have these equations for theta p. Where's the equation? Here, right here. And do the calculation. See if it gives you the same value. It should. Otherwise, something wrong there. Okay, any questions? No? All right, thank you.